What's up? Econ got canceled, which means you can come to this. Woohoo! Good to see you here, Lauren, Aaron, Catherine, Jennifer, William, Cameron, Lauren. Hey, Mewbot's in the chat. Mewbot's awake right there. We got the music, the chill music. How's everyone doing? Yes, I can hear it still. It's possible to do a quiz or the homework? Yeah, we can do quiz or homework. I'll start with some review, then we'll go to quiz or homework. How's that sound to you? I've got some ideas for the review. I want to share my ideas with everybody. We'll mention this in class today, so I might do it kind of quick, but if you're in our class, you'll hear this today. We explained the last one from chapter 12. I understand that it is 1 minus none. I'm confused how you find none. Sure, is it the soda one, or is it the light bulb one? Is it the soda one or the light bulb one? I think that's one of those. Let's start with the review, then we'll do some Mop Pearson. Here we go to the review. Oh, okay, I'm gonna mark this here in the stream. I feel like maybe I do want to put myself here. I'm gonna move myself a little bit on the screen. Because nice when I can walk across the screen, but then again, the way is to be right here. I'm gonna lose a little spice. There we go. Now I can only go to over here. This is where the void ends. Still a lot of room, but now I'm more over here, so when I stand in my normal spot. So is this? It is office hours. Yep, it is. I figured since everyone can see these videos, I figured I'd do a little bit of review to start. It is totally office hours. But I figured I'd mark it as review, maybe more people will watch it, because I want to start off with that. Let's mark this, start a stream. And then right here we are at the 3-minute and 13-second advice for exam 2. Okay, so there's gonna be some quick advice, and I came up with a way I think to do really well on exam 2. So here's the 3 steps for doing well on exam 2. You ready? These are my 3 steps. We'll be talking about them today in class to start. I'll have this written out to start. Who's ready in the chat? I need some I'm readies. I need some I'm ready. I'm ready. Little SpongeBob in the chat. Step 1, study. Well, kind of. This is when you get to the test. So I agree with Cameron right there. Cameron, great job. We'll start some points. So here are the steps. Step 1 is going to be ABC or BCBA. Sorry, CBA. We got to reverse. Reverse. You got to be ready. So it's going to be choose the interpretation. Then blank form, and then add context. Everyone see the CBA right here? Choose the interpretation. What are we talking about? What do you think this relates to? Where you'll have to choose the interpretation, write the blank form, and then give it the context. What's up, Valeria? Good to see you, Reagan. What do you think this is? This is CBA. Which interpretations? What are the 3 interpretations you'll have to do? What are the 3 interpretations? This relates to, yep, the r squared, the slope, and going from memory, might be doing them in the right order. Now, of course, make sure you look at which one you're supposed to do. Slope, the r squared, and what is r squared not? Like when you're interpreting r squared, it's blank percent the variation y, explained by the variation x. Please check out the review 2 videos where I go over this. And I've done them a lot, I've written them a lot. But the number one way, it's not correlation. Great job right there, Cameron. R squared is not correlation. So if you want, go to these review videos right here, because we can do this a ton of times, but it only works when you sit down and you write out the interpretations. Like you can see R squared interpretation right there. It's in this video. You can click through any of these videos, the chapter 7 speedrun reviews, watch them, learn the interpretations, and then don't just look at them, write them down. For 1,000 points, who can write out one of the blank form interpretations? Like show everyone in the chat or who's watching this later, what do we mean by the blank form interpretation? Let's go 10,000 crazy points right here. We're going a little crazy these days before the test. What do we mean by the blank form interpretation? Like, give me one of the, it says choose the interpretation, like choose the r squared, choose the slope, choose the intercept. The question will say interpret this. So you need to know which one you're doing first. That's the first part of this. Which ones do you have? Like give me a blank form. Blank percent of the variation y is explained by the variation x. Boom, blank percent of the variation. Make sure it times it by 100, like whatever the r squared is. If it's 0.68, it's 68%. If it's 0.121, it's 12.1%. So 68% of the variation in whatever the y variable is, height, is explained by the variation in the x variable. Whatever x is, like weight. So with that right there, you're going to then choose, is it one of those 3? It'll be. Then you'll put the blank form, then you'll add the context. Now, what I want you to do, so listen carefully right here, is I want you to start the test. And here's the thing, great job, Jennifer, right there. These are the last 3 questions on the test, so that you are ready and you know what to do at the start of the test This is my strategy for you. You're going to go to what questions to start. Because if you know how to do these, boom, 12 points, you start off like, got that one, got that one, got that one. You know how to do these. Make sure to add, Jennifer put the on average on there. Make sure to tell if the intercept is illogical. If it's illogical, tell us if you think you got points off. Go to the end of the test, get your 12 points, good to go. So that's the first step. You get 12 points right there if you follow those rules or follow this practice that we're doing, 12 points. Here's step 2 to doing well in the test. We're going to call it SD, C, what is it? SD, we got a C. I don't know. I'm trying to think about better. I thought I had something better in my head. I remember I was trying to figure this out. Like, what's the strategy here? SD, we got a C. So kind of not SATA drive. SD, SATA drive, right? This is what I thought of too. But SD, we got a C. We got to see what's on the formula sheet. So when you get, the next thing I want you to do is I think you can Control F or Command F. I don't think that causes issues in Proctorio. I don't think Proctorio is going to get a little mad at a search. Because if you see sampling distribution, sampling distribution is in a problem, where do you need to go? Anytime you see sampling distribution in the problem, so I would do the sampling distribution ones next. So you make sure you're like, these are the tough ones, gonna get these done next. You're gonna have your formula sheet printed off next to you. And here's what I want you to do. When you go to the formula sheet, the thing you're gonna look at for the sampling distributions are gonna be what? So the things you're gonna look at first, it's gonna say like, what is the mean for the sampling distribution of the sample proportion? Can anyone type that in the chat? Like, let's say a question says, what is the mean for the sampling distribution of the sample proportion? You're gonna look at cat or quant, exactly. So the mean for the sampling distribution of the sample proportion is P. Cameron got it right away. Cameron, great work. Wow. Little Owen Wilson to support you right there, because the mean for the sampling distribution of the sample proportion is that quantity, and that quantity is P right there. So great job, Reagan, also. So these are the questions people usually get wrong also, because the notation right there, it takes some practice, it takes some getting used to. So I want you to do the standard or the sampling distribution ones next, and then you say sampling distributions, SD, I got a C, what's on my formula sheet? So we got CBA, check your interpretations, get the blank form, and then add your notations. SD, I got a C, and you'll probably do well. So what do you think I want you to do next? What do you think I want you to do next? What is the mean for the sampling distribution of the proportion? P right there, William got it. So probably do well. Probably do well. What do you think you should do next? I would knock out all these. I'd look through, because this is where people usually make mistakes. Probably do well. Step 3, well, but here's the thing. This is what I want you to do next. These are the orders I want you to do them in. When you get tests, I want you to do some probability next. Because this is where people also make mistakes. But there's some easy ones. Like if we said 2 things that can be easily added together must be, and think of words you could say. 2 things that can be easily added together must be what? 2 things that can be easily added together must be what? Disjoint or mutually exclusive. Same word right there. Disjoint or mutually exclusive are the words we use for that. And look right here, mutually exclusive is the same thing as disjoint. And it's right there with the addition rule. So we know that. When one thing does not influence the outcome of another, 2 events are said to be what? I'm going to give you a tougher one after this. When one thing does not influence the outcome of another, 2 things are said to be what? Independent. Once again, and then 2 things that are independent can be easily whatted together. 2 things that are easily independent can be easily whatted together. If they are independent, we can easily do this. Multiply together. That's the multiplication rule. Well, what about this? Disjoint events are very dependent or very independent. Disjoint events, so I'll write here as a question. Disjoint events, and so be careful, because this is a more advanced question. Disjoint events, ooh. Yeah, well, wait, so Cameron, can you explain it? So remember, it only means this way. It doesn't go the other way, but you are right. Dependent aren't always disjoint. That is true. Like, Brian drinking coffee might depend on his wife drinking coffee, but Brian and Chelsea making coffee in the morning depends on our coffee machine working. If the coffee machine doesn't work, we can't drink coffee. So then drinking coffee and coffee machine working at our house would be disjoint if all of the coffee we have is from the coffee machine. So, but you could, so this requires the more in-depth knowledge right here, if you get what I'm saying, because one tells you about the other exactly. So if two things are disjoint, they are completely dependent. So that's one thing. If things are dependent, it does not mean they are disjoint, like inherently. It's not like dependent means disjoint, but if they are disjoint, that does mean dependent. If you don't get that, don't worry. That's like the highest level of understanding you can have on this. You have to think, okay, if it's 100 degrees out, it can't snow. So those are disjoint. Because if one happens 100 degrees out, it can't snow. That's disjoint. So now it's snowing is 100% dependent on it being 100 degrees out. Because being 100 degrees out means it can't, dependent, did I say independent? Dependent, I think I said dependent. It's 100% dependent. But you could say things that are dependent, like snowing depends on it being below 32 degrees. Could it be below 32 degrees and not snow? Like one thing happens and the other doesn't? Could it be below 32 degrees and it not snow? And it could snow, right? You see this? It could be below 32 degrees and it could snow or not snow. So what I'm saying here is because the other event could or could not happen, they are not what? Be careful, listen to the words carefully. Because it could be below 32 degrees and it could snow or it could not snow. Like either one could happen. They are not what? They are not what? They are not disjoint exactly because the other thing could happen. This happening, the other thing could or could not happen. But it being below 32 degrees would what the probability of snow, meaning it is this. It being below 32 degrees would what the probability of snow, meaning it is this. And this is where you understand the words. It would increase the probability of snow, influence, increase, meaning that snow is dependent on the temperature. You get that, you know probability pretty decently, and that's where I'm trying to differentiate between the words. Be very careful. They mean different things, but then they do coincide a little bit in what they do, but don't think, oh, disjoint means dependent. No, don't do that. Don't do that. Don't do that. I've had people do that, like disjoint is dependent. No. Disjoint events must be dependent. Dependent events don't have to be disjoint. Okay, anyways, that's a quick review of probability. What should we do that first chapter 12 problem real quick? The at least one. Thank you, everyone right there. These are my 3 steps to do well on the test. I want to see if people follow this and they do well. If they do, I'll tell people again next semester to do it. Start at the very end with the last questions, then do your sampling distribution with your formula sheet, then do the probability ones. And here's the thing. Does the formula sheet give you the rules of probability? Rule number 1, that the probabilities have to be between 0 and 1. It doesn't actually give that one. Rule number 2, the set of all probabilities have to add up to 1 if you add up all the sets. Rule number 3, the complement rule. There's 2 versions of it. Rule number 4, the addition rule. Rule number 5, the multiplication rule. We use the or word for addition. Add right there. They must be mutually exclusive disjoint. So when you're doing probability, have your formula sheet out. Focus on the probability questions next and look at the formula sheet. Let's go do that question right here. I got my Red Bull. I already drank it today. What is the last one on chapter 12? Someone said they wanted the last chapter 12. Was it homework? Was it the last chapter 12 homework question? Is that what we're going to do? Is it the last chapter 12 homework? Not this one. Might have been the quiz. How did the question go? And then we can do... Okay, sure. Like an at least one problem, right? So do an at least one problem, right? Okay. Probability of winning something right here. Bring up the calculator. If you've done a lot of the at least one problems, then you can look at it. We're buying a 6-pack of soda. 2, 3, 4, 5, 6. Then you have to ask, how do we do it? So let's look at this question, break it down more in depth. Okay, so how did we do this is always the question. Because if you know how to do them, it's a good question. How do we find none? So here we are with the question. There's the question. You have to imagine that you're buying soda with winning possible caps. What would be the best thing in the world if you bought a 6-pack of soda and 26% were winners? Probability of winning. What would be the best thing in the world? What would be the oh my gosh, you'd be like, oh my goodness. You'd be so happy. Win on all of them. What is the probability of winning on the first and winning on the second? Listen to the words. And winning on the third and winning on the fourth and winning on the fifth and winning on the sixth. What is the probability of winning on all 6? Like you win on the first and you win on the second and you win on the third and you win on the fourth and you win on the fifth. You wonder why I keep accentuating that word. It's right there in the multiplication rule. And then what would each soda bottle say about the previous soda bottle and its outcome? It doesn't matter. Would say it doesn't matter. Now, we're just finding this right now for funsies. We're just not even worrying about what the problem says. We're just saying the probability of winning and winning and winning and winning and winning and winning and winning, maybe 6 times, is going to be 0.26 to the 6th power, because it's the probability of winning 6 times in a row when each turn of the cap is independent, which we will assume it is. Not that they, I mean, it could be. We don't know how they do it, but we're going to assume independent, which means one win does not influence or make you more likely to win on the next one. Not exactly what we're finding yet, but that's a good starting point. Probability of losing is going to be the complement of winning, because either you win something or you don't win something, which is lose. There are ties in games, but for this, we only have win or lose. So what is the probability of winning something, or losing something rather? What is the probability of losing something as I try to, oh my, there we go. Really? There we go. What's the probability of losing something? I'm having fun. 0.74. Either you win or you don't win, which is lose in this instance. So 0.74. So what's the probability of lose and lose and lose and lose? You open your first cap and you lose, and you open your second cap and you lose, and you open your third cap and you lose, and your fourth cap and you lose, and your fifth cap and you lose, and your sixth cap and you lose. So if you work that out right there, the probability of losing all 6 times, the first time you lose, and then the second, and the third, and the fourth, and the fifth, and the sixth, it's 0.74 to the 6th power, which is 0.74 times 0.74 times 0.74. 6th power just means a series of that. Now, here's one thing to know. If you ever do something like this right here, why would you immediately start to say, So if you do something like this right here, why do you immediately go like, yeah, I don't know. Here, we'll go over here and we'll do it. A lot of people do this by accident. They go 0.74 times 6. And what do you say? You've broken the first rule of probability. You say, uh-oh. You say, I did something wrong here. Then you go look at the formula sheet. What's wrong right here? What's wrong about 4.4? It's more than 1. Probability must be contained between 0 and 444%. Oh my gosh, it's over 9,000. Not quite, but close. So Jennifer right there, great answer. That doesn't make sense. And also Sarah, great answers too. And Lauren right there, good work. So that doesn't make sense. Don't do that. It's technically multiplying by itself, which if you do that a bunch of times, it'll be to the 6th power. So now we have the probability of losing 6 times in a row. So how about this? You will either lose all 6 times or win something. Does that make sense? You're either going to lose all 6 times or win something. And this is what that could occur. This is the writing the sentence that is usually the hard part for people. Why do I write 1 right there? Because that is what? You either lose all 6 times or you will win something. You will either lose all 6 times or you will win something. Because you're going to either win something or you're going to have all losers. You can write all losers, but it's lose all 6 times. It adds up to 1. Like, this is everything that could occur, so we put 1 over here because it's the complement rule. Like, you're either going to lose all the time or you're going to win at least once. So this is the sentence you need to know how to write. And once you write this sentence, you just take right here, and the or becomes a plus because or means addition if they are disjoint, which they are. Then we can subtract this from both sides. Technically, I would write minus here and minus here on the other side, but it subtracts off itself. And now we have 1 minus lose all 6 times is the probability of win something. And that's where we found this to begin with. And we just plug that in right there. We'll do this. And we'll plug this in so you can see the series of steps to achieve the answer. And there is the answer right there. At least one win. At least one win is everything but 6 losers. So if something occurs outside of losing all 6 times, you will win at least once. Does that make sense right there? Really good question, really good practice. And the more, like, who's gotten, don't worry if you can't do these quickly right now, but has anyone been able to do these really quickly when you see it? You're like, okay, I'm either going to lose all 6 times or win once, and then check your work, because sometimes people do the reverse way, because if you know the trick to it, you got a 50-50 shot. Because if you know it's like 1 minus the probability to the power of times, you got a 50-50 shot even if you just remember that. Like if you remember this formula right down here, 50-50 shot. You just got to figure out which way to go, thank you, Sarah, right there. Good work, and good to see you here, Mary Ellis. So, yep, need a second to think about it, but yes, no worries. Don't worry about being quick. Be careful. I've had people make 80s who are like amazing students. They're like, I just flew through the test, and I'm like, just take your time, rework it, write it down, think it out. You got a lot of time on the test, so make sure you take your time when taking the test. And if you do have additional time and it's not there, please let us know immediately. This would have made math class so much easier in high school. I've always struggled with probability until, oh, thank you, Jennifer. That's such a huge compliment. Thank you, and Sarah, good luck tonight. I think when you turn it into words and look at, like, try to figure out what you're solving for, then it makes more sense. Like, what am I trying to find? What's the point of this? And then you think about it visually here, like, well, either I'm going to lose all the time or I'm going to win at least once. Thank you so much. I like when people say, oh, it makes sense. That's the biggest compliment I got from someone was like, oh, neural networks now make sense. And I was like, oh, cool. I like that. Michael, good to see you there. And so now let's go. Are we going to do chapter 14 homework? Should we do the full homework? I think we've done some of it. Let me put a poll up, homework or quiz, and we'll do that. So homework or quiz, we're going to do chapter 14. Homework or quiz, and I should have marked this as at least one practice. I'm going to take a guess at when we started it. I started at 16:13. So the quiz, people are voting the quiz. Okay, let me get the quiz going. Chapter 14 quiz. Oh wait, did I do the wrong one? I think I did the wrong one. They did some weirdness with chapter 14 a while ago. No. It used to be sampling this. Can we go to the grocery store receipts question? Sure. Is that chapter 14 one? I'm trying to remember. They did this weirdness where they used to do sampling distributions together, and then now they put the quantitative one together, or the categorical one together, and the quantitative one together. That's why 13 and 14 are split up between 2 different tests. The grocery store. The grocery store question. Let's find it. Okay, so what should you have open beside you? What are you going to have open beside you while we do this? I'll get most of these done. Yeah, we can do this one pretty easy. What do you have? If we are able to do the practice exam, would you be able to say probably? Probably. The better you can do it without the help of the videos. You might overfit though. Like if you do it a bunch of times, you're like, I can ace it. But have your formula sheet beside you, and doing the practice exam is a good sign for the test. Can't promise you'll do amazing, but good sign for the test. Chapter 14. Quiz, a grocery stores. Okay, so don't even look at the questions yet. Here we are. We are doing the sampling distribution of the sample what? Mean or proportion? Are we doing the sampling distribution of sample mean or sample proportion? We're looking at how much customers purchase. And they purchase on average $26 with a standard deviation of 14. We are doing the sampling distribution of the sample mean. So if I got a question like this, here's the thing, usually when we do work, it doesn't usually tell us, we come up with our own questions in analytics. So what I would do is I'd say, okay, so if I know from this data the following information, well, it says here that there is a slightly skewed distribution. So the customers we select would need to be what kind of customers right here? We're reviewing for the test right now. The customers we select would need to be what customers? We're going to look at what we would expect from 309 customers. Doesn't quite say it, but we'd have to assume what about these customers? First thing, condition 1. Once again, don't worry about the question. Worry about, do you know how to do this? We'll answer the questions here in a second. They have to be random customers. They can't be like, it can't be a sale on Sunday. It has to be, Sunday is a random set of customers. So, okay, good. As long as there's randos right here, we're good. And what about the 309? The 309 needs to be what? These need to be random customers. And the 309 needs to be what? Condition 2. We need these to be random customers on Sunday, like random individuals. They didn't come in for a sale. They're not like representative of Sunday shoppers. They're representative of all our shoppers. Less than 10% of the population. So you'd have to assume we have more than how many customers here? You would have to assume that the population, because that's the sample size right there, you'd have to assume our store has more than this many customers. So you can times it by 10 right here, and you'd have to assume we have more. Exactly, great job right there, Sarah. More than this right here. Now, what is, so we just did condition 1 is random. Now, what do we do? Put them in the chat. Put those in the chat. Get ready. What do you do when you get, before you do condition 3? 3%, literal 3%. What do you do before you get to condition 3? What do you do? You pause, you put those pause in the chat. And with the pause in the chat, we ask ourselves, is this categorical or quantitative? Cat or quant's not here today. Maybe I'll go wake him up a little bit later. But you go ask yourself, is it cat or quant? And we're doing how much people spend at a grocery store, their purchases. And so purchases is going to be what? I'm denoting, kind of we're making a choice right here by the color coding. So purchases is quant. So now the last condition is large enough n. Check out a lot of our videos where we go into more detail on this. The large enough n condition is lowercase n. This is large enough sample size, caught some people on the practice or during the quant, so large enough condition exactly. And so we have to look at the shape, know the amount, and check it. What is the shape right here? The shape is what of this? What is the shape of it? So the shape, we need to look at it. It's skewed, and the amount we would need because of the shape is 25, and our amount, our n, is way greater than 25. So n is greater than 25, which n is equal to this right here, and we've marked that right there. A little color coding to help out, but 309 should be way large enough, way large enough. So because of this, because we meet all 3 conditions, we can now draw the what? Because we meet all 3 conditions, we can now draw the what? Good review of conditions right here. We didn't do success failure because this is the sampling distribution of the sample mean for quantitative data. We can now draw the normal curve, and we're good to go. So the normal curve, we'll recopy this question. That was just a review of conditions, very important for the test. We can now figure out the mean, and mu is going to be kind of mu. But the mean for the distribution of the sample mean is going to be equal to what? The mean for the distribution of the sample mean is going to be equal to what? The mean for the distribution of the sample mean is going to be equal to what? Read your formula sheet now. The mean for the distribution of the sample mean is going to be equal to what? And what I'm saying is, I'm saying it's mu, great job. The mean for the distribution of the sample mean, or the expected sample mean, can also be pronounced that way. It's going to be mu, and then the standard deviation is going to be the original standard deviation over square root of n right there. So we grab these off our formula sheet. So if I were you, you can't copy paste from the test, but you're going to look at exactly this line of data right here, bring it over, make it all look nice and pretty. So with this right here, this is exactly what we need. So that's what you want to do right there. You want to be like, this is the information I need. And now we're going to go right here. And it literally says the mean is this. So that is the mean, and we're trying to find that quantity. It says the standard deviation is this. That's the original standard deviation. And then, there we go. Now we're going to plug in our values. I'm just taking the highlighted values, plugging them in right here. So mu y bar equals $26, and SD y bar equals 14 over square root 309, whole quantity square root. Oh my gosh, what am I doing? Look at me, I was thinking p times q over n square root. What's that like? It's gonna be like 0.8 or so, 0.82, I say 0.82. I drank a Red Bull this morning. Had my brain say 0.82. I'm sorry, Cameron, I'll do better. I say 0.82. How'd I do? Me. Look at slacking. I was off by 3 hundredths or 2.5 hundredths or so. Now, I wouldn't, I'm going to write this down as 0.80. I should have just said 0.8 because it rounds to that. But carry your decimals. Great job, Cameron, right there. Carry your decimals while doing this. This is where you wouldn't be doing this on the test, but we can use the applets right here. So what you could do is you could draw this on the test. You could draw this. I can also make educated guesses. So this is what you would not do on the test. I'm just showing you what I can do by thinking this through. So let me look at what the question says and see how much I can get with just using my mental math. Estimate the probability that the store's revenue is 8,300. So 8,300 divided by 309. Oh my gosh. That should be a pretty high probability. I don't know. Estimate how much does it make on the worst? Oh, the worst, wow. The worst is going to be $12 about. The worst 1%. No, 2.32. So it's going to be 12 times that. This is a very hard, like if you don't use the applet. Okay, we're going to get it wrong. 2 decimal points. There's my guesses. We'll see how close Brian is. Got 0 right, but now let's go take a look. Hey, Olivia, good to see you here. So this is where we need to go to the applets. And we could ask you things like z-scores on the test. Maybe I'll make a z-score version of this. But notice what we're going to do is we're going to take the mean and then plug in the standard deviation right here. And I usually do this. Don't do that. I usually put it on both of these curves right here. It is on both. Adam made it that way. Does this make sense? We're plugging in our numbers. And now what we have to do is this. We have to go to the question. So plug your numbers in. And now we say at least $8,300. That means on average, so watch this right here. There's a key part of it. $8,300 means on average, divide by 309, you'd have to make 26.86. Oh man, that means it's going to be very close to, if I get that right, I'd be very happy. That's a much better guess now that I'm able to do that. So let's go over here and put in the value for the average that we have. So I found out on average, we need to make at least this. Oh man, I could have just put 14% and probably got it right. So there it is right there. This is what we needed to make. This was the amount divided by the amount of receipts. So take the number 8,300 or so divided by 309. Find out on average. I saw it was a little bit above 1 z-score. That gave me a decent guess. It is basically 14%, so I was very close. I probably could have typed 14 and gotten that one right. So my second guess, being able to see the z-score, because I know what the standard deviation is, it led me to a much better guess on this, and I got a lot closer. So now we have here the worst 1%. So this goes to your knowledge of the normal curve. Is the worst 1% on the left or the right side? Is the worst 1% on the left or the right side? You have to click over to here. Is the worst 1% on the left or the right side? The worst 1% on the left or the right side? The worst, it's on the left side, right? So that means we need to enter in 1% right here. And this is what, and then we need to go to the other side of the curve, or we can enter 99. I'd probably enter in this and then make sure we see that. And this is how much we'd make on the worst 1% on average. And then we times this by the 309. So take that value right there because that's the average times by 309, 7,461. And I was close-ish, not super close, but close-ish, and that should be right. Very good question, pretty tricky. But it could ask you this. The store had, think of this, you ready? The store, I think I said tip. The store had sales that averaged $28, or let's go 29. The store had sales for these 309 customers that averaged $29. Was this unusual and why? So now this is more of a test question. From the sample of 309, they saw $29. Was this unusual and why? So try to think this through and tell me what you've done. Because I can, yeah, it's going to be about 3.8 or so. You know where I'm going with it. So the store had sales of 29. Was that unusual? This is what you can do on the test. The stores had sales of 29. Was this unusual and why? Jennifer, keep going. Yep, and find it for me. I think it's gonna be about 3.8 or so. And then find the z-score, right? Because it is more than 3, so what you would do is you would take observation of 29 minus the mean of 26, divide by the standard deviation. I said 3.8 or so, carried your decimals, and it's 3.8 when you round it. Does that make sense? So I'm moving it over in my head, and also if you draw the curve, you can see 29 is off the curve. It's above the third standard deviation. Great job right there, Sarah, and that's exactly what to do. Do you know what most people do when they get to this question? Is they don't use the new standard deviation. How do you think many people would solve that if it said something like here, like on the test it could say, is an average from 309 of 29 unusual? What do you think most people do? A lot of people get to this and they say, oh, that's not unusual, because what do? They use the given standard deviation. Exactly. So it would be for the 309, the average of 29 is unusual. They use the population standard deviation, which is a very common error on these. They use the $14, and then they're like, oh, that's like a z-score of 0.5, or 0.4. That's not unusual at all, or very small, like 0.3. So be very careful. Get the new standard deviation right there, and then if you notice, it is in the formula. It is there. There's the standard deviation of 0.80. So then you take the original, the mean of 29, if it says there's the mean, and then subtract off. So that's how it could be on the test. That's why we write our notation first. Cameron's got it down right there. Notation, brother.
Notation, brother.
I'm going to fix that between office hours here. More points in the chat. We need to make up some more levels. Which question should we do next? That was a really, really great review question. We've done the waiter or waitress problem a few times, so we've done this one a lot, and it's very similar to that last one. Which one should we do next? I want to see who has the Cameron's about to hit 1,000,000 points. Oh my God. I know, Cameron. I just saw it too at that moment. Lauren's got some amazing points. So, and we got to come up with some new levels because, like, yeah, and I've been breaking the point scale. Help people hashtag show up. Which one should we do next? You name the problem, we do it. That was a really good problem. Oh my God, look at all those points. Should add some new levels. What problem should we do next? You name it, we do it. We got time for probably 2 more at least. Which problem should we do? Any problem. Waiter, waitress, waiter. Okay. So the first thing we do when we get to a problem like this, the waiter, waitress problem, classic right here. Thank you, Catherine. So the first thing we do when we get to a problem like this is what? I know it's a fun question. Waiter, waitress. Heading to class. You're welcome, Sarah. Good luck in class. Hope it goes well. The first thing we do is what? Think really hard. We go like notation. Ooh, I like that. Let's do that here in a second. You got it. $11. I'm trying to figure this one out. I'm going to figure it out. 70 cents. Okay. Best 1% of weekends, 70 cents, 72. Close as I on this. Oh, I can't use my calculator. No calculator, no calculator. Okay, I'm trying to do the math, then we're going to solve it. 72 times 2 point, oh my God. So, taking too long. That is going to be about 1.8. That's 12.4. 12.4 times 50. Cut it in half. So 12.4 cut in half is $612. Okay, so here's my guesses. Let's see how close I get by doing it in my head. Ready to really solve the problem now? Let me put the real timestamp for people who want to see the actual work. That's as close as I can get with no calculator. Now let's talk about how to solve it. Repeat.
Notation,
what's the first thing you do? Because I was looking for this. The first thing you're going to do when solving these problems is get what? The first thing you're going to do when getting these problems is look for the what? The notation. So I was able to identify, and these problems are here, and great job, Lauren, right there. I was able to say that this right here is the mean, and this is the standard deviation, which is sigma, population standard deviation. This is the amount of tables, which is 50, and this is how much it would be the sum of, that's a sum, sure, that's a summation. Sum of the y variable of interest is equal to 550. The sum of the y variable, and this is going to be equal to going here to the curve and taking the top 1% right there. That's what that means. So we've got everything marked on the screen. We just now need to go to our formula sheet, and a clue for this one is that you've marked sigma, and you're talking about tips, so you want the sampling distribution of the sample what? You've marked sigma, and you're talking about tips, so you want the sampling distribution of the sample what? You've marked sigma, and you're talking about tips. You want the sampling distribution of the sample mean. So this is a huge clue right there. As you can see, I had the highlighter clicked. There we go. That sigma right there alone is enough to point to, you're talking about the mean. Be careful. Standard deviation does come up otherwise. That is the population standard deviation though. So now we can find these other quantities. Mu is very clearly mu. So this quantity right here is 10.60 in dollars. And I got about 70 cents or 72 cents when I did square root of 50, square root, and then 5.10 divide by, and I was getting 72 cents. That's what I was finding in my head. This formula right here is the 5.10 divided by square root of right here, the 50 tables. There we go. And that is equal to about 72 cents, but carry all your decimals as you're doing this. So carry the decimals on that. And now this is where the problem would be a little bit different if we were doing it on the test. Where do you think I'm going to go right now? Where do you think Brian's going to go right now? Wild guess if you look at the chat. Wild guesses. This is where I could ask different things on the test, but right now we're going to go over to the applet. We're going to immediately plug in these numbers right here that we got. Was it 10.50 was the mean? I think it was. And then the standard deviation is not that. It's this. And let's double check our numbers. 10.60 right there. Now, what the question wants is it says she wants to make $550. You won't use the applet on the exam. You would do things like the previous problem where I asked you for the z-score. So look for things like that. And I could end this one with a z-score also. So you won't use, or you could show you a picture on the test of the applet, or we could actually the mean, the standard deviation, things like that. So now she wants to make $550. So she wants to make $550 on 50 tables. What should I do to figure out her average tip? She wants to make $550 on 50 tables. How can I figure out the average tip she wants? She wants to make $550 on 50 tables. Divide by 50. Great job, Zoe, right there. So there's $11, and then we go to this one, find p-value from x, and we go above this value right here. Now I noticed the z-score is about 0.4 if you look at this. That's something you could find right there. And so knowing that, I took a guesstimate of what it was, and it's 29. I think it said 4 decimals, and this is the answer right here, and that's how to do it. So here's the first problem right there on the screen. And my guess was, did I say like low 22s? Not, I mean, what do you think? I said 34%, it's 29%. I was off by 5%. Decent guess. That's a harder part of the curve to get right. But here is my guess again. There's my guess. It was this right here. And here's, so I said 35 and it's 29. Decent guess. Now we go and we look at the next one, the best 1% of weekends. Now remember what we put on our notes? We drew this right here, which is the best 1%. Oh, really? Oh, man, I was really trying hard in my head, Cameron, on that one. Yeah, I mean, I can solve it now by hand, actually. Here's the thing, since I know that standard deviation, watch this, then I'll do it. Thank you, Cameron. Square root of 50, 5.10 times this, and wait, what did I do? 5.10 divided by this, and now times 2.3263 plus 10.60 times 50. There it is, right? Wow, it was close, right? So there's the answers, but how did we get this? Okay, well, the thing is I know the z-score 2.3263 by memory. So let's show how you would do it without knowing the z-score for the best 1%. The answer is, and thank you, Cameron, I was really close to it. And Cameron, we're throwing Cameron 50,000 points. Cameron already worked this problem as we were working it, and that's where you know how to do it. Because we want to go over here to the applet and take the information we have on the screen and go to find the x using p-value. So we're going to go to the best 1%, which is going to be on the right side of the curve. So we want to go to the 99th percentile. And this is not how much we make. Thank you, Karen, right there. This is not how much we make. This is what? Oh, you hit the 1 million. Yeah, nice job, William. This is not how much we make right there. This is our average tip on 50 tables. So since that's our average tip on 50 tables, we times it by 50, and that gives it right there. So 613.90, which usually there's a little bit of leeway. Oh, there we go. We got it to the dot, or we could have rounded it up to this right here, and that's the answer. Does that make sense? Little tricky problem. We've done it a few times, so I always like to mix it up. I like to challenge myself to see if I can do it without the applets. That's the fun part here. Can we just, I was trying to just do it in my head, be like, can I just figure this out just looking at it? Can I like think it through? Because people are like, well, if I don't have the applets, I'm like, you can think it through. Just study these things for a decade plus, and then you just see it. I don't know. Don't do that. Don't study the same topic for a decade. You'll become me. Next question. But you can do these without the applet. But we on the test would ask you for things like z-scores. Another one. I like right there. Oh, that was the baby thing, right? When we did that. What's another good one to do? A lot of these are very similar. Okay. I like this question. I think it's a good, like, when do we use the central limit theorem? What two things does the central limit theorem state? What two things does the central limit theorem state? What two things does the central limit theorem state? What two things does the central limit theorem state? The distribution of the sample mean or the sample proportion will become more normal and tighter as n increases. So you could have a distribution that looks like this, ridiculously skewed. And if you were to take 5 observations and find the mean, that's a sample mean right there from 5 sample data, and repeatedly do this process, the new distribution down below will be more normal and tighter. So notice the standard deviation got smaller by a factor of the square root of 5. We could actually show this mathematically here. So go ahead, and when I solve, anyone ever wonder what well, we got to find square root of 5 first. 9.69. What is 9.69 divided by square root of 5? I bet it's 4.34, and there it is right there. Ooh, wait a minute. See how it's not the same? And now we got to wait just half a second. Oh, there we go. Oh, it did it. But it should, if we go to infinity, law of large numbers, there we go. And it should stabilize on that 4.33. I always hate it when it doesn't do exactly that. It's just we got to do it a lot sometimes. And in class, we had to do it a ridiculous amount of times. Now, this is for a sample size of 5, but we might need a bigger sample size depending on how skewed it is. Notice there's still some skew. Does everyone kind of see that little bit of skew? Notice how there's this, it goes bump 1, bump 1, bump 2, bump 2, bump 3, bump 3, bump 4. There's still a little bit of skew. So this is a heavily skewed distribution. Let's say that's still skewed down below. We probably need a sample size of what? That's heavily skewed. We probably need a sample size of what? I maybe figured out how to do this now. Let me go and make a... Yeah, it's stabilized. Darn you, central limit theorem. I'm trying to make it so it doesn't work. I'm always trying to do that. Darn you, central limit theorem, probably 100. So the more skewed it is, the larger n needs to be. This is a heavily skewed distribution up top. It's right to the high because Monster Man right there, he's got a right skew. The simulations will show the central limit theorem, and notice at the end, and here's the thing, this is ridiculously skewed. So since it's ridiculously skewed, skewed is 25, very skewed is 100, insanely skewed would have to be way more than what? Like, I mean, just come up with something here, because the more skewed it is, the larger n needs to be, so that's the original data. And notice here, at a sample size of, this is 200, right? At a sample size of 200, it's still too skewed, so we'd need even more larger n. So the simulations do support the central limit theorem. Now the peak is where the mean is, so the mean will do what? This is another thing to remember. Yeah, 1,500. It's theoretical. You have to kind of do it and see if it does it. So there's no hard and fast rule. It's kind of like, well, take a look at it and see if it's normalized. It's just the more skewed it is, the larger n needs to be. And Williams said the mean stays the same. So the mean stays about the same. The shape will become more normal right there. And the variability is going to increase, decrease, or stay the same? Variability is standard deviation. So does variability increase, decrease, or stay the same? Variability is standard deviation. And standard deviation is getting divided by the square root of n. There's the mean staying the same over there. The variability spread is decreasing by a factor of square root of n. So we know that via the formulas, and that's what's happening right there. So it's going to decrease. Someone says a rule of thumb is, hey, if you got 30, 30 is always large enough. Would you be like, yeah, cool, or no way? 30 is always large enough. Like with a sample size of 30, you're good. It'll normalize. No, it's heavily, if it's really skewed, 30 is not large enough. So the sampling becomes less. No. Yeah, it doesn't apply to heavily skewed distributions. So you'd have to look at the shape of it first. Like, is it very skewed? This only applies to quantitative data. So we knock out one more, we'll have done half the quiz. So this one is just a lot of finding. That one's a lot of math. I mean, it's not bad, but it's the same as that one. Same. And this one right here, I mean, it's the same as the previous one. That is only a little left skewed. So notice that you need a what or n. This one's only a little left skewed. I know, right? You just got to know the formulas. And Cameron, great work right there. This one's only a little skewed, so you only need a smaller n. So these simulations do show the central limit theorem. All the histograms are centered around this because the mean stays the same. As n gets larger, they become more normal. So approaches the normal shape. The variability decreases. The histograms become normal. Yeah, so it doesn't take a very large n because it's not skewed at all. Seeing how much we can do. We did this one. This one's on the homework too, right? We did this one on the homework. Well, I guess let's do this one right here and we'll finish off with it. Because we've done the other ones on the homework, so if you've, now all the questions are in the video. Almost all of them are also on the homework. I know, right? So like, we also did some in class, right? If you practice these, you'll get them down. And even if you don't ace the test, I've seen this. So let me mark this so people can hear this in the video. People who get over, like I think a 95 on my Pearson, next to no one makes lower than a B. So if you do well on my Pearson, I can't promise you'll make a B in the class. Good luck, Olivia. Thank you. Oh, Olivia, former student, right? Thank you, Olivia. Olivia, drop them some advice right there. I'm like, I haven't seen that name in a while. Thank you so much, Olivia, right there. We're going to do this researcher question to end. But thank you, Olivia. You can see your old level maybe if Mubot hasn't updated it. If you do points really fast. But I might have deleted your points. I was like, I haven't seen Olivia in the chat in a long time. Thank you, Olivia. We're reviewing for exam 2. You probably saw by the video title. Let's see. Is it an old school ultimate Blake level? In Mublox are 0. No! It'll reverse because of that. Take a screenshot right there. I undo the Mublox every semester because people, well, now I don't need to if I'm not teaching other classes online. But with, I know, Olivia, let me fix that for you. Olivia, we're going to fix this, and then we're going to do this question. So Olivia, give me just a moment, and we're going to fix this problem. Take this very serious. And Olivia, check your points. Check your points now, Olivia. I think you're the new point leader. So here we go with this question while Olivia checks her points right there. We got the central limit theorem here asking about the theoretical mean and the theoretical standard deviation. So with this, oh my, Olivia's leading the way with like 999 million points. Ridiculous. Let's go. And then it'll change to the meme tier level. You'll get a new level when Mubot sees that. He'll update levels. Cameron right there. That's when you really become the Stat Nation legends. I can update points. Oh my, I know, just got like 1 billion points instantaneous. Researchers measured the waist size of 249 men, the true mean and true standard deviation. Now, when you hear the true mean and the true standard deviation, what do you think of instantaneously? When you hear true mean and true standard deviation, you're hearing mu and sigma and you're hearing waist size. We're talking about studying for the test right now, so what do you think? What do you think? Mean. Cat named Quant, we're thinking quant right here because this is waist size, which is quantitative. We got the true mean and the true standard deviation. So now we know the true mean is equal to this, and the true standard deviation is equal to this. So really the only hard part about this is you have to go through repeatedly and do sigma over square root of n for each one, which is going to be, simply put, 4.008, and you're going to divide by square root. Does everyone understand where I'm going with this? It's just the same thing repeatedly. Can I copy this? I can't. Here we'll write it 4.800, 4.80, 4. There we go. And so that's the new standard deviation. Notice it is going to get smaller. The good news for us, though, for finding the mean stays the same because the mean doesn't change as we increase our sample size. So we can write 36.446. Copy that down. The mean stays the same, and the standard deviation gets smaller by a factor of square root of n. So square root of 2, 1.414, I think so. There it is right there, and we need to divide 4.008 by this. There's the new standard deviation to 3 decimal places. Fun times. Next we have 5, which is 2 point something. So 5, 2.3, 2.2. So 4.004. Oh my god. There we goes that. And remember we wrote the formulas down the other screen. That doesn't look right. That got way too small. 4.008 divided by this. Something weird's going on. Square root of 5. 4.008 divided by this. That looks better. Your standard deviation should get a little smaller each time. So if you saw something weird like I saw, then you've done something incorrectly. 4.008 divided by that. And once again, it is getting smaller. You can take a guess. Next one's going to be close to 1 probably. 20 square root. And then 4.008 divided by that. And it is kind of close to 1. And then to 3 decimal places right here. There we go. Should have that right. Now here's the thing. We could look at it, but simulations show us what we would see in reality. So the theoretical values are going to be reasonably close to what we see, and the standard deviations are going to be reasonably close. Looking at the histograms about when do they become normal. Ooh, really? You're going to make me judge this? 5 and 10 look good. What do people think? 5? What do people think? 5, 10? 5? Yeah. I mean, it's just more normal at 10. It's definitely normal at 20. Since this is, the smallest shape at which it is unimolar and symmetric. Thank you so much. I think people have done this quiz already. Yeah, it's like, truthfully on the test, I wouldn't love that as a question. It's like, 5 or 10. It's not that skewed, so the n doesn't need to be that large. Yeah, regardless, the sampling distribution is unimolar and symmetric, so sampling distribution sample mean does not need to have a large sample. And we've done it. So we've done all but 3 questions, and if you're looking for the other ones, they are in the video. Are people feeling pretty good about the test? We did some review. We're gonna have class here in a moment. So swing by class. We're gonna be reviewing. We're gonna start off with those 3 steps to do well on the test. Jennifer, great job. So get ready. I'll see everyone here in a little bit. Outro for now. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.